So the next piece we're talking about is the chain rule. This is another shortcut to allow us to do the derivatives of some uglier things that we haven't been able to do in the past. For instance, if I gave you something like 2x minus 4 to the 4th power, what would you have to do to be able to do the derivative of that? FOIL it all out and then do the derivative of each term, which is no big deal if it's a square, but when I throw in a 4th or an 8th or something like that, that becomes extremely time consuming. And so we need a better option. So that's where this chain rule comes in. Now, I want to show you something first. We've done the derivative of something to the 3rd power before. I made you write it 3 times and we did the product rule 1 at a time. So u to the 3rd is just like u times u times u. So if you did the derivative, you do the first, the second 2 stayed the same. Do the derivative of the second, first and last stay the same. Derivative of the 3rd, first 2 stay the same. Those 3 terms are all the same. If you combine them, you get 3u squared times u prime. Or that can be called 3u squared times the derivative of u in terms of x. That kind of shows us the chain rule. So here is the big result here. If you have this capital F is representing a composite function, so a function inside another one, you can do the derivative of the outside, the inside stays the same, times the derivative of the inside. You might also see it written with the dy dx's. I don't use that notation as much, but I really talk about it more just we're going to do the derivative of the outside, inside stays the same, times the derivative of the inside. So that example that I threw up here, if I wanted to do this derivative, the derivative of the outside thing is the 4th power. When you do a 4th power, when you work that derivative, the 4 comes down and you subtract 1, right? So derivative of the outside, so the 4 comes down, inside stays the same. We have to subtract 1 from the power, times the derivative of the inside. The inside in this case is inside my parentheses. What's the derivative of 2x minus 4? 2. So this derivative actually turns out to be 8 times 2x minus 4 cubed. And we don't have to multiply it all out first. Any questions there? So that is the big thing we are doing today. Let's look at another one. The key to being able to use the chain rule is understanding the difference between the outside function and the inside function. What's the outside right here? The 17th power. So when I do this derivative of the outside, so if you have something to the 17th, the 17 comes down, inside stays the same, subtract 1 from the power, times derivative of the inside. So my inside is the 3x squared plus 5. What's the derivative of that? Oops. And then I would like for you just to do the basic multiplication to clean it up at the end. Questions there? Just as a notation thing, that second notation I gave you with the dy du and the du dx, those aren't fractions, they represent derivatives. So it's the derivative of the y in terms of x and the derivative of that u in terms of x. So you do have to watch, just remember with that notation, you're not just canceling things out, you are doing derivatives along the way. Alright, so pretty much the rest of the day we're just going to practice chain rule. If I look at this one, how do we typically start out if a problem has a radical in it? Change it to a what power? 1/2. Okay. So my derivative of the outside, so 1/2 comes down. The inside of the parentheses stays the same. Subtract 1 from the power. Times, what's the derivative of this inside? Multiply 1/2 times 2x would just give me x. It's x squared plus 1. So negative 1/2. We're finding two different things in here. How are those different? A and B with right. On the first one I'm squaring the x, the angle. On the second one I'm squaring the sine, the trig function. Okay. So on A, what's the outside function? Think about it, if you were going to plug something in, whatever you would do first is your inside function. If I plugged in a pi, what would I be evaluating first? The x squared. So the x squared is my inside, which means the sine is the outside. So chain rule says derivative of the outside. Derivative of sine is cosine. Inside stays the same, so my angle is still an x squared. Times derivative of the inside, 2x. So we just get 2x cosine of x squared. On B, keep in mind what that means. When I have a sine squared, that means you are going to take the sine of x and then square your answer. So the inside function, if I plugged in a pi, what would I do first? The sine. So the outside is the square. So chain rule, derivative of the outside. So the outside is squared. We know something's squared, the exponent comes down. Inside stays the same. Subtract 1 from the power. Times the derivative of the inside. Derivative of sine is cosine. So we just get 2 sine x cosine x. So derivatives are very different here. That's why it is extremely important when you are working with these sines and cosines, you put your square in the proper spot. It's a lot different to have an angle squared than it is to have the trig function squared. Any questions there? The next slide, I think I'm going to skip. It's just kind of a result that we're already using anyway, so I think it's easier if we just kind of gloss over that. We don't really need it as a separate piece. Okay. Let's look at this one. An oil refinery makes U liters of gasoline from X barrels of crude oil. So U is the number of liters of gas they make, X number of barrels of oil it takes. Then they make Y grams of petrochemical from the U liters of gasoline. Identify the units of dy du, du dx, and dy dx. So I'm not asking you to calculate anything. I'm just wanting you to realize you could look at just this expression itself and know the units for your derivative. That's why proper notation is so important. A derivative is just a rate of change. So it's going to be something, the division is like per, and then something. So if I look at this, what are the units for y? Y is grams, so it would be grams per, for my division, u. What are the units on u? So grams per liter would be the units on that derivative. You guys do the second two for me. Just identify your units. U is liters per, X is barrel. So how many liters per barrel they are making. Dy dx. So Y is per, X is, so grams per barrel. Is all that okay? Why don't you guys do the next, three examples, 5, 6, and 7. I want you to practice doing your chain rule. Catch mistakes. So when I'm doing this derivative, outside is the 100th power. So the 100 comes down, inside stays the same, subtract 1 from the power. Times, what is the derivative of x cubed? 3x squared. Derivative of 1 is 0, so we can ignore that. So our actual derivative is 300 x squared times x cubed minus 1 to the 99th power. Example 6. Again, we have something to a power. So the exponent comes down, which is a -3. Inside stays the same. Subtract 1 from the power. -3 minus 1, -4. Times derivative of the inside. Derivative of 5x squared. Derivative of 2x is 2, and the plus 5. We're going to take a short. So from here, you could do a little bit of simplifying. You don't necessarily have to, but it wouldn't take much work just to run the -3 through this parenthesis. So it's kind of up to you how much cleaning up we do. But if we distributed that, we'd have -30x plus 6 times the 5x squared minus 2x plus 5 to the -4. Okay, example 7. So for those of you that just came in, we're doing the chain rule. So it allows us to do the derivatives of something like this without writing it 3 times and multiplying it out first. So the idea behind the chain rule, you do the derivative of the outside function. So if you think about this, there are 2 things going on. You have the 2x minus, or the 2 minus 5x, and then you have the third power. So the third power is the outside part. So derivative of the outside, if something is to the third, you would bring the third down. In the chain rule, that inside piece stays the same. and then we subtract 1 from our power. So that's the derivative of the cubed portion. You with me there? And then you do times the derivative of just this inside. So derivative of 2 is 0, minus derivative of 5x, so I just get a negative 5. So overall my derivative is negative 15 times 2 minus 5x squared. So far so good there? We are going to do a few more examples. If I gave you this one, we have really two options. We could do the quotient rule, or since it's just a 1 on top, how could I rewrite this? Right. Do you want to do the quotient rule, or do you want to write this as a negative power?
Negative power. Negative power.
I'm glad we all agree. So the derivative. Derivative of the outside. So the outside is that negative 2. So the negative 2 comes down. Inside stays the same. Subtract 1 from the power. Negative 2 minus 1 is negative 3. Times derivative of the inside. Derivative of 2x cubed is minus derivative of x is 1. I'm going to go ahead and just multiply these pieces together. You don't necessarily have to. So it'll give me a negative 12x squared plus 2 times the 2x cubed minus x plus 7 to the negative 3. This one. We're getting into some uglier ones now. We have a couple options for how we might work this problem. We can keep it as it is, as 1 thing to the 5th power. We could choose to do the top to the 5th and the bottom to the 5th. Either way, we're ultimately going to end up doing the quotient rule. So it really doesn't matter to me how you want to write it. So do you want to keep it as it is, or do you want to put top and bottom each to the 5th power? Okay. So you don't have to, but we have that option. So the derivative. The big thing we're doing here is I have something divided by something. So my big thing is I have to do the quotient rule. Quotient rule is low d high, derivative of the top. What do I have to do to do the derivative of the top? Chain rule. Okay, so the chain rule says derivative of the outside, so that's the 5th power. So my 5 comes down, inside stays the same, subtract 1 from the power, times the derivative of the inside. That's just a 1. So this blue right here represents the derivative of the top of that fraction. So everybody with me there. Kind of doing the chain rule within our quotient rule. So we're doing more than one thing at a time. So we have low d high minus high d low. So now I need the derivative of the bottom. So to do this, because it's to the 5th power, we have to do the chain rule. So the exponent comes down, inside stays the same, subtract 1 from the power, times, what's the derivative of the inside? 1. All over low We have a lot of cleanup to do here, so neatness is going to be your friend. You need to be able to read your handwriting to clean this up. So as I'm working through this, on the top, I'm going to pull that 5 just out in the front. Then we have the z plus 1 to the 5th, the z minus 1 to the 4th, and then I could just drop my times 1, can't I? So all I did right here in this first term was got rid of my times 1, and then I just moved the 5 out in the front. I'm going to do the same thing in the second term, so really just reordering. I'm going to pull my 5 out in the front of that, and my z plus 1 to the 4th, and then we can drop the times 1. On the bottom, if you square this, how do you do a power to a power? So that's z plus 1 to the 10th. Okay. Anything else we can do there? Yeah. We have a z plus 1 everywhere, don't we? So we can cancel how many of them? 4. Cancel the smallest power. So 5, if I got rid of 4 of them, that just leaves me with a z plus 1, a z minus 1 to the 4th, minus 5, I had the z minus 1 to the 5th, and I canceled that term. On the bottom I had 10 of these, but I canceled 4 of them, so I'm left with 6. There is more we could do here. We could factor out a z minus 1 to the 4th on the top, multiply out what remains and get some terms to cancel. I would accept your answer like this. When we get to the point where we're going to do higher derivatives, we might try to simplify a little more, because the more you simplify, the nicer the next derivative will be. But at this point, as long as you canceled anything that shows up in every term, I would be satisfied with your answer. Okay, so you could leave it like this for now. Questions on that one? Last problem of the day. What am I going to have to do on this one? We've got this times this. So my big thing I'm going to have to do is product rule, because I have things being multiplied. So product rule is the derivative of the first. So to do the derivative of this piece, exponent comes down, inside stays the same, subtract 1 from the power, times, what's the derivative of the inside? So this blue represents the derivative of that one. So derivative of the first times the second, plus the first one, times the derivative of the second one. So derivative of this, the 2 comes down, inside stays the same, subtract 1 from your power, so now it's the first. Derivative of the inside there is not a whole lot we could do to simplify here. I'm going to multiply these two pieces together because the 1 plus 2x doesn't have an exponent. So that would give me a 5 plus 10x. X plus x squared to the 4th, 1 plus x cubed squared. 2 times 3x squared would be 6x squared. X plus x squared to the 5th. 1 plus x cubed, and that was just to the first. You could even distribute the 6x squared to this one. This is kind of the point, if you haven't noticed, where we are rapidly getting to the place where there might be 3 or 4 different answers that are all equivalent, just depending on how much you simplify your final